I'm Professor Rad, and this is Precalc video 2.5, 3 theorems. So in this video, we're going to be talking about 3 theorems about polynomials, including the fundamental theorem of algebra. Are you guys excited? I'm excited. So before we build up to the fundamental theorem of algebra, let's look at these first 2 theorems and see what they mean and how we might be able to apply them. So these 2 theorems do not have names. If you want to pause the video here and copy them down, we can do that. Hopefully you've copied them down if you wanted to. Let's go through theorem 6. So in theorem 6, a polynomial function of degree n has at most n unique roots. So what that means is, let's say, I have an example here somewhere. Yeah, so let's say I have something like x to the 5th minus 2x squared plus 16. Okay, and I wanted to factor this. What that means is if I were to factor this into linear factors, it would have at most 5 such factors. So at most, we'd have something like x minus, I'm just going to call it a1 because I don't know what it is, x minus a2, all the way up to x minus a5. Now, what this means is I don't have to factor into 5 roots, but if I wanted to know like the maximum number of x-intercepts a function could have, right, because x-intercepts and roots, we're going to think of those as the same thing, way back from Theorem 2, the following are equivalent. So if I want to know what's the maximum number of x-intercepts I can have, it's the same as the degree. Okay? So that also helps me know like when I'm done factoring. Theorem 7 also helps us know when we are done factoring. So Theorem 7 says that every polynomial function with real coefficients can be uniquely factored into linear and or prime quadratic factors. So what this means is, let's say you're factoring a polynomial and like you want to know, okay, am I done? Have I gotten to the end of my factoring process, or can I break this down more? The answer is yes, if all you have left are linear factors or quadratics that don't factor. So for instance, if I have something like x plus 1, and I'm continuing to factor something, and I end up with x cubed minus 1. Okay, let's go with x cubed minus 4. What Theorem 7 is saying is that I'm not done factoring. I have a linear factor, but this cubic, this can be factored more. So this is not prime. And I know it's not prime because it's not quadratic, it's not degree 2. So this theorem says we can keep on factoring this. And in the next video, we'll talk about, how to do that factoring, how to factor polynomials that when we look at them, we're like, we're not quite sure. We're going to put all of our tools and techniques together to do that. So that's Theorem 7. All right, so now let's look at the exciting theorem. Alrighty, so here we have it, the fundamental theorem of algebra. Where's that music coming from? So our fundamental theorem of algebra says that every polynomial of degree n greater than 0 can be factored into n linear factors of this form. Okay, and in this format, what they're telling us is that A and each of these R's are complex numbers. So this fancy looking C means complex numbers for all of those subscripts. So the previous theorem, Theorem 7, said that we can factor into linear and quadratic factors if we're only living in the land of real numbers. What this theorem says is that we can factor so that we get complex solutions. We can factor completely. Now, when you have a fundamental theorem of a particular field of math, it's called that because it means that was a significant and important turning point in that discipline. So when you get into calculus, for example, there are going to be fundamental theorems of calculus, and those are big, important concepts of calculus. So this was a big, important foundational theorem of algebra where it signified kind of like a turning point. You can think of it as like the world, the universe was limited to real numbers, and you can't factor everything over the real numbers. So you can have prime quadratics, right? You can have parabolas that don't have any x-intercepts. But if we expand our concept of what a number is outside just the real numbers, if we now involve complex numbers, so things like 3 minus I or 7i plus 15, if we account for those complex numbers, now you can factor everything completely. So, for example, if I'm expanding my world to the complex plane, if I have something like x squared minus 7x, let's do plus 7x. Let's just do plus 7. Let's do something I can think of reasonably here. So if we have x squared plus 7, this is a parabola that's smiling and is shifted above the x-axis. So this cannot be factored in R, but it can be factored in C. So we can find the complex roots of this, and we can use the quadratic formula to get there. Now, notice what's different about this theorem from Theorem 6. In Theorem 6, we were talking about unique solutions. So you have at most n unique factors. So same thing here, you're going to have at most n unique factors. So in this case, when it says n linear factors, it doesn't mean you have unique factors. You could have some repeats. So for example, let's do for instance here, you could have a polynomial that when you factor it looks like 3 times x minus 1 times x plus I times x minus I times x minus 1. So this polynomial is factored completely, but you'll notice some of the factors are not unique. We have a repeat. So x minus 1 has repeated. So all that this theorem is stating is that if I have a degree 4 polynomial, I can break it down into 4 factors. Some of those factors might be unique, like plus I or minus I here, and some of them might be repeats, like the x minus 1 and the x minus 1, it repeated. All right, so that's it for this video. Pretty short and sweet, and we got to hear about the fundamental theorem of algebra. So that's a nice majestic note that I think we should leave on. So in the next video, we'll be looking at all of our theorems put together and combined now to factor a polynomial and to ultimately solve polynomial equals 0. So I'm looking forward to working with you with the culmination of all this work in our next video. In the meantime, I hope this helped you with some of these theorems, and have a wonderful day. Bye for now.